Question of DC motor. Okay, I am reading the problem just.
Okay.
Sir, a 10 HP 230 volt DC shunt motor has armature resistance of 0.1 ohm and field resistance 180 ohm.
Okay.
At no load,
Sorry to interrupt. Could you please present it?
And sir, actually I have a in written form, so I have to take the pic and then show the screen.
That should be fine. Or if you can type in the chat box also, that is another option. Anyway, you are comfortable.
Okay, sir, I am typing in chat box.
Okay, good. Okay, so in the meanwhile, I think I should present my screen. So I you are able to see my screen. So in this problem, let us discuss this problem.
Sir, I have said in chat box.
Okay, let me see. Fluxes speed. Okay, so is it fine if we take this problem after solving 2-3 problems based on such concepts? So it will be easy for me also to make you understand.
Okay, sir, sure.
I have taken is from the last year's assignment. Okay, so most of them were based on such concepts what you are asking right now. So it will be easier for me as well to discuss. This problem is based on a DC shunt motor with the voltage of 200 volt, has an armature resistance of 0.1 ohm and negligible armature inductance. So it was okay and running at 900 rpm. When the field flux is suddenly reduced by 15%, the load torque is constant at 15 Newton meter. Okay. We have to find the maximum armature current immediately after the flux change. 900 rpm should be the rated value. Okay, this section should be separate, and this section should start when the field flux is suddenly reduced by 15%. How much armature current will be there immediately after this incident? Okay, so I think there is some incorrect arrangement of the problem statement, but anyway. So I hope you got the idea right. At rated condition, it was drawing 15 ampere of armature current and running at 900 rpm with 200 volt of DC voltage. And load torque is constant at. We have to deal with, we have to find out the maximum armature current, and armature current we know In case of motor, Vt minus Eb by Ra. Since we have shunt motor, so shunt motor will look like something else. So your RF, this is Eb with some armature resistance, and this is your V2. It will draw line current. There will be some component of line current will go into field current, which will establish the field flux. Some armature current will be a circuit of shunt field motors will look like, and at rated condition, what let's compute what was the back EMF, because we have the information of VT, R, and A. So back EMF minus IRA. VT is 200 minus IA was given 15 into RA was 0.1. So it will come out to 198.5 volt. Okay, till now it is fine, right? Now in Newton meter, also it is equal to K5 A. Right? We know, we can compute K5 value, right? And here 5 is stated. Right? So K5 rated will be how much? 15 by 15. It will be equal to 1. Okay. Now, when you had the rated condition, now field flux is suddenly reduced by 15%. And to maintain the same speed, that you need to find according to this problem, right? So what will happen that first we will find out what will be the back EMF, because when you are reducing the flux by 50%, the problem when field flux is not anymore rated, and what should have happened, but speed we are maintaining constant, and torque is also 15 Newton meter. Okay, so to cater the 15 Newton meter of torque, there will be huge current required. Okay, so let me find out through the equation how much that current will be. So to find out the current, we need the back EMF value at that instant of time. So let us compute EB2. It will be how much EB1 into by. Is it fine? Any doubt till this point? You can ask anytime. You can stop me in between as well. So I'm hoping it's fine till now. Now, even we have computed that 198.5 into 52 by 1. Since 15% is reduced, so it is now 0.85 of 1 is equal to 1. If you compute this value, it will come out to be 168.725 volt. Okay. Now, so you can see that reduction in flux is directly reflected into the back EMF. Now, because of this reduction, load torque. Okay, we will compute IA2, that will be Vt minus V2 divided by Ra. Vt is then 200 minus 168.725 divided by Ra is how much? 1 312.75 amps. Current has been increased from 15 amps to 30, higher than 20 times of the rated current. Okay, and it is not a desirable phenomenon. That's why we introduce some series resistance. Okay, why series resistance and why compound generator or compound motor we use? If you would had some series resistance here, and this series resistance would have limited this current. Okay, field series compound kind of motor. Okay, but anyhow, in this problem it is not the case. So you have to pump in 312 amps of current into the circuit to maintain the load torque. Okay, any doubt in this part?
Hello.
Okay, so to maintain the same speed you have to pump in much current. Now the next question is, at this current, how much electromagnetic torque will be generated? How much torque at this current? So for this purpose only, we had found out K5 rated, right? We had found out this value K5. So we will do torque is equal to K5 into I8, K5 2 into I8. Now K5 was 1. Now flux had been reduced by 15%. So we can write it as K5 2 is equal to 0.85 into K1 into I8. We know 312.75. It will be equal to 265.8 Newton meter. Okay, that torque will be generated to maintain that speed. You are reducing your flow. It is ideal to maintain the rated flux below the basis till the basis speed. Otherwise, you will have to pump in so much of armature current to compensate that reduction in flux. So 15% reduction in flux will cause you more than 20 times current. Not desirable. Okay.
Sir, they did not mention speed is constant.
Sorry, what is constant?
Sir, speed.
The speed.
Yes, sir.
Sorry, I couldn't get your question. Could you please repeat it?
Sir, they did not mention that speed is constant.
Your voice is breaking. I don't know why.
Sir, he is asking about the EB1 and EB2 formula. Sir, while using that formula, you have assumed that the speed in both the cases will be same. He is asking for the reason, sir.
Okay, okay, okay. So even if you do not assume the speed is same,
Sir, your voice is breaking, sir.
what is happening when you are reducing flux, your EB will change, right? If you reduce your flux by certain quantity, right? So what will happen? It will be reflected to back EMF. And since it is mentioned that your motor is running at 900 RPM, isn't it? Your motor has to run at 900 RPM. It is not saying your flux is reduced so you can reduce your speed as well. The load torque is constant at 15 Newton meter. It means when you are reducing your flux, would have been there had not been any issue. But now
Sir,
your motor, yeah,
sir, your voice is breaking.
I think your network is poor. Neeraj, could you please confirm my voice is breaking or not?
Yes, sir. Your voice is breaking. I just rejoined this session, but it is again happening in.
Okay. Let me see. Now, could you hear me?
Yes, sir. Yes, sir.
Okay, is it better, right?
Yes, sir. It is better from previous.
Okay. So what I was saying that in the problem itself, it is mentioned that your flux is reduced immediately, right? So uh, see, if your motor is running at certain speed, now you are reducing your flux. That is very easy. That is the electrical domain that you can easily tweak it by changing your field current, isn't it? You just reduce your field current, your flux will be reduced. Very simple. Now, that effect of that reduction in flux will be transferred to mechanical domain, which is your rotor. It's rotating at certain speed. It will take some time to come down to that speed. Okay. Since your rotor is running at 900 RPM, and you see that's why the terminology is used here, suddenly reduced. Okay, suddenly reduced. So it is asking about transient condition, not about steady state. In a steady state, we will see what will happen in the same problem. But in transient, your field flux is suddenly reduced, but your rotor speed will not be suddenly reduced. It will take some time to come down to that value. And during that transient, what will happen? Your motor will draw huge current. To prevent that huge current, we use such a resistance limiter, right? So this problem is awareness about, difference, time constant of electrical and mechanicals are very different. In electrical, it is very small time constant, but mechanical, it will be almost 10 to 20 times of that electrical. So it will take some time to settle at the steady state. If you are doing some changes, there will be some transient. After that period, it will come to the steady state. And in the same problem, you will see in the steady state what will happen.
Okay, sir.
Okay. So that's why I had to assume because of 900 RPM. Otherwise, in a steady state, of course, there will be different scenarios. So in transient period, it will draw such a huge current of 312 amps and 265.8 Newton meter. Okay. Now, the next part we have is estimate the armature current. What will be the armature current at a steady state? Now, what will happen?
Sir, I think it will decrease.
What will decrease?
Current, armature current at a steady state.
At steady state, armature current will decrease from this to 312 amps, right? Not from 15 amps.
Yes, sir.
Yeah. So see now what will happen. And one thing I want to ask you beforehand, that what will happen to speed now? Since you have reduced the flux, what will happen? And in last session also I posed this question for you. You remember the last question? I told you to analyze before base speed, after base speed, what will be the conditions? To think about it, right? So again,
Sir,
here you have to answer.
speed is inversely proportional of flux. So then, if flux will reduce, speed will increase.
Okay.
If power is constant. If power is constant.
If power is constant. Okay. So could you guess here what will happen to speed? Will it increase or decrease in a steady state? Since you have reduced the flux, okay, you have reduced the flux to 15% by 15%, right? So what will happen now? In a steady state, a speed will be at rated, or will it reduce, or will it increase? Because to maintain the steady state, you have your there after that mechanical time constant over a period of time, your rotor will settle to the different speed, isn't it? And if your motor will be settled at different speed, then what will be that speed? You just have to let me know whether it will be higher than rated, or lower than rated, or rated, or it will be keep it will still at 900 rpm.
I think it will be higher than 900, sir.
Yeah, because you have reduced the flux and you are keeping the same, or even you are maintaining the torque, right? So what will happen? Let us see. Okay, in this section. So first, what we will do to maintain the same torque, okay, what we have to do, according to the problem, we have the load torque is constant. So load torque is again what? K phi Ia is constant, right? Now phi 1 Ia1 is equal to phi 2 Ia2. Phi 2 by phi 1 we know is 0.85, so Ia1 was 15, phi 2 by phi 1 is 0.85, Ia2. According to this equation, Ia2 will be how much?
17.64.
17.64 amps, right? That much of current will be there. Now, because of this current, we have to find out, or because of this condition, when load torque is constant and mirror flux is reduced, we will have new back EMF, which will give us the new speed, right? Because back EMF is always linked to a speed. So back EMF will be, new value of the back EMF will be Vt minus Ia, that is 17.64 into Ra, 0.1. It will lead to how much? 198.2. See, so in a steady state, we have got the reduction in back EMF from 198.5 to 198.2. So only 0.3 voltage of difference. Okay. This 0.3 volt of difference will lead you to certain new speed that we will compute it here. EB2 by EB1, phi 2 N2 by phi 1 N1. Now you just plug in, right? 198.2 here, 198.5, phi 2 by phi 1 is 0.85, N1 was 900. What will be the N2? So N2 will be equal to approximately 1057.4 RPM. So at steady state, the rotor will be settled at 1057.4 RPM. Okay, so this will be the speed which the motor will operate at in the steady state. Okay, is it fine? Deepak, are you getting it?
Yes, sir.
Any question in this?
No, sir.
Okay, great. So again, after settling at this speed, I am introducing the new condition again for the transient period. Okay, what will happen when, you know, now at this condition, again your field flux is brought back to its initial condition is equal to phi rated. Okay, what will happen now? During transit, suddenly, so it is, you know, it is transient based question. So your speed will be same. Okay, your flux will be increased. Now what will happen? So what will you do? You have to follow the same pattern. Now what first thing what we will do? Since your flux had been changed, okay, and you are tweaking your electrical parameter, and because of this change in flux, the thing which will be reflected for constant, you know, constant torque. Anyway, in transient it doesn't matter because in transient nothing will happen suddenly, right? So back EMF will be the parameter that will be affected immediately. So again, EB3 now I will name it. Okay. EB3 by EB2 is equal to phi 3 by phi 2, and phi 3 here will be 1, phi 2 will be 0.85. EB2 already we have computed 198.2 volt. Now we have to find out the EB3. And if you calculate it, you will get approximately 233.2 volt. So now your back EMF is higher than the terminal voltage. Now in this transient mode, your armature will be delivering the current to the terminal and it will behave as a generator. Okay.
Sir,
Yeah.
sir, in this case, we have assumed that phi 2 is a less than 15% less than y phi 3.
Hmm. Uh, in last case, what happened that it was at 85% of rated, right? Now you are bringing back the rated flux. So now our phi 3
Okay.
is the rated flux, and previous condition phi 2 was equal to 85% of the rated flux.
Okay, sir.
Okay.
Yes, sir.
Now, because of this back EMF, what will happen to the armature current? EB3 minus VT by RA, right? The direction of current will be this.
Change.
Yes. Right? So EB3 we have computed 233.2 minus 200, 5.1, and it will lead to 332.2 amps. Again, huge current will be drawn during the transient period. Right? Now again, the same phenomena will happen. Again, you have to settle at a steady state with constant load torque. So same thing, you can repeat it, and same thing happens in the practical application of motor, right? You give some certain input, control input, some transient will occur in the machine, then it will settle at the steady state. Then again, you will give certain another input, and this phenomenon will recur, right? Is this clear? This is how your speed control of DC motor will work.
Yes, sir.
Okay, great.
So,
Yeah, any question,
so
Neeraj?
is there any possibility of damaging the windings due to these high currents, sir?
Definitely, there is high possibility of getting damaged. That's why
Sure.
I mentioned in between that that's why we use series resistance, right? To limit that current. Though it will reduce your performance by a few margin, but it will protect your motor.
Okay, sir.
Okay.
Okay, sir.
So generally in practical machine, we do not have such kind of a spike in the current, and we do not want it as well. That's why we use certain protections as a resistance and other things. But just to emphasize this problem, this question was given. According to this numerical problem, you could uh, visualize or analyze what are the problems and why you should appreciate the series resistance you use in that machine.
Okay, sir.
Okay. So
Sir,
again,
when
we have yeah. Go ahead, please.
sir, when we were reducing the field current, sir, then the field flux should also be reduced with some delay, sir, as the inductance of the coil will come into the will have this
Yes.
effect, sir.
That's why I mentioned that electrical time constant. So when you are changing, it will reduce according to the electrical time constant. That is your L by R, inductance of the circuit and resistance of the circuit,
Okay, sir.
isn't it?
Yes,
But
sir. Yes.
your mechanical time constant is way higher than this.
Okay, sir.
Okay, great. So this is the next problem. Okay, here we are inserting some resistance in the shunt field to raise the speed. So basically, what happens when you insert certain resistance in the field? So I'm asking this question: what do you expect from machine to behave when you are inserting certain amount of resistance in the field circuit?
So field current should decrease,
Field current will be decreased. Exactly.
then therefore field will be weakened.
Field will be weakened. It means flux will be reduced, right?
Yes.
Yeah. So that's what we are gonna do in this problem. So initially 230-volt DC shunt motor were taking 30 amps of armature current, okay, and running at 600 RPM. So let me draw again the same circuit. So this is how your circuit will look like. Now, initially, R external was 0. So, and your field resistance is 230 ohm and supply 230 ohm. So I field 1 230 by 230 it will be 1 amp, and the speed was 600 rpm, and 30 amps of armature current it was taking. So IA was 30 amps, IA1. Okay, fine. At constant load torque. Now, minimum resistance need to be inserted in the circuit so that N2 will be 700 rpm. So it means your rated speed was 600 rpm. Now you have to increase the speed, so you have to operate in the field weakening region. So by how much factors should you reduce your field current? Okay, and that resistance should be minimum resistance. Okay, so what should be your approach? How to proceed this particular problem? So let us see if rated is equal to KIF rated. Okay. Now, first find out at 600 rpm what was the back EMF. At 600 rpm, the back EMF was 230 minus 30 into RA is how much? 0.5. So 3 into 5, 215 volt, I guess. Yes. So 215 volt. At 215 volt, the speed was 600 rpm. Flux was rated. Okay, this we have got the information. Now, from the second condition, we have 700 rpm and flux would be something we don't know, and EMF also we don't know. Okay, we just know that our speed has been increased. Okay, so but one information is given in the problem. If you know the current, okay, then you can easily find out the EB2. At EB2, you can easily find out VT minus IA into RA. But current is not given in the problem, right?
So torque remains constant. We will use the
Oh,
torque formula,
yes,
sir.
yes, exactly. So your load torque is constant. So since torque is constant, then it means K phi 2 into IA2 will be equal to K phi 1 to IA. IA1 was given 30 amps, right? Now what will be IA2? IA2 will be equal to 30 into phi 1 by phi 2, right? Yes. So IA2 we can say that phi 1 by phi 2, and yeah, fine. And now EB2 also we can say EB2 by EB1 is equal to phi 1 into phi 2 into N2 by phi 1 into N1. So EB2 also we can say is equal to phi 2 by phi 1 into 700 by 600, I guess. Yes, 700 by 600. So EB2 is again 7 by 6. 5 2 by 5. So we have back EMF and current in terms of 5 2 by 5 1. So let's suppose we name it, right? We should name it as 5 1 by 5 2 as K. Okay. So it will be 7 by 6K. Okay. That
Sir,
makes
where,
sense.
sir, EB1 term, where is this?
Okay, EV1 term I think I have left. So EV1 was how much? 215. Yes. Thanks for reminding. EV1 was 215 into 215. So now how much it will be? 215 into 6 divide, I'm sorry, 215 into 7 divided by 6. So it is 250.83. Okay, now I think we are fine. So now we can equate EV2 is equal to ET minus IA2 into RA. Okay, EV2 is 250.83 divided by K is equal to VT is nothing but 230. IA2 is 30K. 30K, right? Yes. Into RA is 0.1, sorry, 0.5. So you will end up having a quadratic equation. So 15K square, 13 into 0.5, 15K square minus 230K plus 250.83. So you have this quadratic equation, you have to solve this, okay? And if you solve it, can you solve it right now? Equation 5, 3. So A is 15, B is minus 230, C is 250.83. 15.
Sir,
Huh.
sir, K is 5 2 by 5 1.
K is 5 1 by 5 2, I guess. 5 1 by 5 2. Yes.
Okay, so here will be opposite. Okay. Yes, sir.
Yes. So how much did you get? You must have got two values of K. Okay. One is 14.15, other is 1.18. Okay. So we end up having two values of K. Which should you consider?
Sir, less value, less.
Why?
Because, sir, the ratio of two flux should be near to equal 1.
Mm-hmm.
I don't know what.
Okay. So basically, yeah. Actually, both are valid values. Okay. Both are valid values. For if you reduce 14 times of the rated flux, also it is fine. But if you are reducing 14 times rated flux, it means you are increasing 14 times your speed if you are maintaining constant power. But here the speed has been just increased by approximately 1.2 times. Okay, 600 to 700. So how much? Let me tell you. So 7 by 6. So it is approximately 1.16 times. So it is close to this value, 1.18. Then we can say that, okay, this value is valid. This value is also valid. You cannot say you can simply discard it. Okay, in subjective type of questions, you should not write that we can easily discard this value and we can proceed with the 1.18 value. Okay, both are completely fine, completely valid values. But the ratio of speed increment should be, in the range by which you are changing the speed. So in that sense, 1.18 is the, reasonable value. Does that make sense?
Yes, sir.
Okay. Any question in this?
No, sir.
Okay, great. So still we haven't got the answer, right? The question was to find the minimum resistance inserted in the shunt field circuit. So now, as we have earlier mentioned that phi is equal to k into if, right? So phi 1 by phi 2 is 1.18. It means phi 2, the new flux we have is phi 1 by 1.18. Okay, so the new current, field current, should also be equal to if by 1.18. Is there any problem? I am simply writing directly. Okay, if not, then if1 was how much? 1 amps, I guess. Yeah, 1 amps. So if2 will be 1 by 1.18. And to flow such amount of current, we need certain resistance, right? Initially, it was 230 plus R external. Okay, I hope you are following. So it will lead to certain value at 230 plus R external. 230 plus R external is equal to 230 into 1.18. R external would be equal to 0.18 into 230. How much it will be? 41.4 ohm. Okay, so that much of external resistance you should have added to operate at this speed, right? Is there any doubt in this problem? I hope you got how did we calculate external resistance.
Sir, why we did not multiply by 1.18 in IF1 because it is reducing.
See, phi 2 by phi 1, phi 1 by phi 2 is 1.18, not phi 2 by phi 1. And phi 1 is the rated flux, right? We have considered. So we cannot use the rated because field should reduce, right? The field has reduced here.
Okay.
Okay, great. Any final doubt in this problem?
No, sir.
Okay, great. So moving ahead, let me take the problem.
Sir, IF1 was 1.
IF1 was 1. If you see the question,
Okay.
IF1 is nothing but VT by RF, right? So field resistance was 230 ohm.
Yes, sir.
Okay. So now here comes the next problem. Again, 240 volt of DC and motor will take 16 ampere of current from the supply, and it will drive at constant load torque at 300 RPM. Constant load torque, okay, 16 amps, 240 volts. Now armature resistance is again 0.5 ohm. Field resistance is 240 ohm to make 1 amps of field current rated. Additional 240 ohm of resistance you are inserting in the field circuit. So if you are inserting additional 240 ohm of resistance, then your the speed will be approximately twice of the rated. Okay, approximately. I am not saying exactly. It will be around that value. Okay, that you can judge from the question, right? Because you are inserting the same amount of field resistance. So basically, you are reducing your field current by half. And
Yes, sir.
field current is proportional to flux, but it is not a linear relationship. There will be saturation in the circuit, so that you have to consider. But you can judge, you can say that it will be around twice of the base speed. So now first part is you have to find the current that motor will take from the supply. Okay, when you have inserted that amount of resistance to maintain the constant load torque, how much value of current that motor will take from the supply. Okay, so let us proceed with if1 was 1 amps initially. Now if2 is 0.5. Okay, now initially ia1 was 15 amps, but ia2 we have to find out. Okay. Why I wrote ia1 is equal to 15 amps? Because again, if you draw that circuit,
So 16 minus 1.
16 minus 1, exactly. It EVRA 240 ohm, 240. Okay. So now IA2 you have to find out. So for constant torque, phi IA is constant. Okay. So phi 1 IA1 is equal to phi 2 IA2. Okay, we can write it. So phi 2 by phi 1 we can write as 0.5, right? So IA2 is equal to IA1 into phi 1 by phi 2. So phi 1 by phi 2 we can write 2. IM1 was 15 into 2, it will be 30 amps. Any doubt till this point? No doubt, because we have solved two. Yeah, any doubt, please?
No, sir. No, sir.
Okay, great. So now moving ahead, uh, how much current it will take from the supply? So isn't it pretty obvious how much current it will take from the supply?
Double.
No, from supply. IL2, we have to find out this
30 plus
current.
0.5.
Exactly, 30 plus 0.5. So approximately double. Okay, sorry, 30.5. Okay, we are done with it. Now, at what speed now it will operate? That is the interesting part. N2. When you have inserted the resistance, now at what speed it will operate? So how should I proceed?
Sir, sir, back EMF.
Yeah, whenever the speed terms come, then we have to directly jump to back EMF, right? So EB1 was how much? 240 minus 15 into 0.5. 240 minus 15 into 0.5. So it
230,
uh, 232.
232.5.
Yes. Now EB2. Same 240 minus 30 into 0.5. So it will be 25 volt. Okay. Now EB2 by EB1 is equal to N2 phi 2 by N1 phi 1. Phi 2 by phi 1 is 0.5. N2 by N1 we have to find out, right? EB2 by EB1, we know EB2 is 225, EB1 is 232.5. So N2 by N1 is equal to 2 times 225 by 232.5. So it will give you something 580.6 RPM. So it is approximately double the rated speed, not exact double, but approximately close to that value. Okay, so in MCQ type of questions, if you are given with such options and those options are not very close, then you can just see the problem and just pick the answer. Okay.
Okay, sir. Sir, sir, flux be considered only produced by the field current, not armature, not by the armature.
Yeah, in DC current, flux is only produced by the field current, not armature.
Okay.
Because your armature is, if you see your you do not have any demagnetizing component until some shifted the axis, right? Or any magnetizing current. Both axes, let me explain you. Both axis, field and armature, is 90-degree apart, isn't it? Until you have
Yes,
some
sir.
shift. Yeah. In synchronous machine, you will see some cross magnetizing component, demagnetizing and all. But in DC machine, that's the best thing about DC machine, that both are decoupled. The armature current and field current both are decoupled. There are no relation between each other. So that's very, very salient advantage of the DC machine. If you want to use ever the DC machine in any kind of traction application where you want to control field separately and current, armature current separately, this is the best machine. And all the advanced control of all the advanced machines, that basically what they do, they decouple the armature current and field flux so that they can control it very simply. So that's the whole purpose of control of all the advanced machines.
Sir,
Hmm.
sir, is this DC generator still used for electroplating purposes, or it has been replaced by some other device?
Actually, I am not aware about that electroplating application. So I cannot answer you, but I think you can easily find out on Google. Just right now, I'm not aware about that particular application.
Okay, sir.
But uh, uh, what do you expect in that application? What are your outcome in that application that you can uh, judge on the basis of that? So was there any drawback using DC machine in that particular application?
No, sir. During these problem solving sessions, it has been repeatedly said that DC machines are going out of use, sir. So therefore, I suddenly that came to my mind that for electroplating or electrolytic cells, sir, DC currents is required, sir. So
Uh-huh.
therefore, I think it is still used there. I was confirming by asking you,
Okay. Yeah, see,
is it still in use?
DC machines are becoming obsolete. That's not a new thing, but it cannot be replaced from everywhere. There are
Oh,
problems with brushes, sparking and all, but people have come up with very advanced design of commutators and brushes so that they can induce such kind of sparkings and all, because we have been using DC machines for more than 200 years. So uh, don't you think that there must have been certain improvements in that industry? There will be,
yeah.
because if you counter any problem, you must find some solution. So there is nothing like, it's up to you. It's completely up to you that what machine you want to use. If
Okay,
let's say for tomorrow you want to use certain machine and you become a giant in some field. Let's suppose today if I'm just giving you an example, you might be thinking that all the industries, big electric vehicles, all are using PMSM, right?
Okay, sir.
Nowadays, induction motors are also becoming obsolete from that application, because nowadays not many companies are using induction motor for their application. Or for example, your synchronous machine, conventional synchronous motor, which has a field winding and armature winding.
Okay, sir.
Okay, but see, recently many giants, many big EV companies such as Audi, BMW, they have used current excited synchronous motor.
Current
So
excited synchronous motor.
what is current excited synchronous motor? On field winding, you are exciting it with current. Okay, just the conventional with brushes and commutators. So on field winding, you have current excited field winding, right? Just like DC motor. And on armature, you have armature winding. So you are not using
Okay,
any
sir.
permanent magnet. So it is your conventional synchronous machine which you study in undergrad, which had been used for 200 years or more.
Okay, sir.
So what would you say that the synchronous machine is now not anymore used? It is being used. So it's completely up to you. Okay. So do not believe on such jargon. Okay, they are true up to certain level. They are true that many people do not prefer that, but there are some pros and cons of every choices.
Okay, sir.
Okay. So let's
Sir,
get back to, yeah, please.
sir, earlier had DC motor cam or AC?
Earlier, what do you think? What would have come?
Means whenever the scientist has search of the motor, they did search DC or AC firstly.
Earlier, we had what kind of supply?
Sir, I don't know.
No, you should know. You are an electrical engineer.
Yes, sir. So
So,
AC.
do you know about the conflict between Tesla and Edison?
Tesla, Nicholas Tesla is no, sir. I don't know much about that because
Okay, you don't know about that. Okay, so you should definitely study about that. So there was one big fight between them, and that fight
hmm.
was regarding DC and AC, which is better. If you are an
Okay.
electrical engineer, you must know that thing, or you can watch a movie based on that as well. So initially DC motor was there, sorry, DC supply was there. Okay, then Tesla came and he said that AC is much, actually both were there, but DC was initially much more convenient. Okay, AC came later, and hence DC motor was the first motor. And then of course the concept of AC get introduced later, so AC machine become relevant later on. And when it became relevant, then it dominated every field, most of the field. That's why induction motor become so such prominent motor everywhere. It replaced all the motors. That's why we call induction motor as a work power of the industry, because everywhere you see induction motor is there. So, yeah, but initially DC motor was there. I think it was in late 1800s or so. DC motor was introduced.
Okay.
So yeah, that was it.
Yes, sir.
But not much later. Both were like simultaneously. But yeah, initially DC motor was there, then induction motor, and after that.
Okay. Sir,
Okay,
induction
so
motor is searched by the Faraday.
induction motor was searched
Faraday's
by the
law.
oh, not law. I'm talking about who was the inventor of that.
Okay, sir.
Okay.
Inventor.
Who brought the idea for the first time of induction motor?
Yes.
So
Tesla,
you,
as you
yeah,
said.
yeah, of course. So you should study a bit of history, right? Because history is what, it gets repeat after a certain point of time. So anyway,
Sir,
so
this history is available on Google or on any other platform. Google.
everywhere it is available, right? It is the most, you know, what to say, most buzz kind of subject in electrical engineering.
Okay.
Okay then. So coming back to this problem, 250-volt DC shunt motor is used to drive a load which has a constant torque. At no load, motor takes 2 amp of armature current. Okay, in last session also this question was right, that at no load certain armature current will be there. So hence it is 2 amps of armature current is there and it runs at 1200 RPM. Armature resistance is given as 0.5 ohm. When load is applied, the motor takes 15 ampere of armature current. Okay. Now 3.5 ohm of resistance is inserted in series with the armature resistance. Okay. Now, what will happen to the no load speed? After the insertion of that 3.5 ohm of resistance. So again, we
So
have
no
to
load
find
speed
out
will remain the same, sir.
no load
Sir,
speed will
increase.
remain the same. You are saying increase. Okay, we will see what will happen. So see, basically, you do not need to guess here. It is very straightforward. You are being asked about a speed. So the first thing what you should do, you should write equation of back EMF. Can we write 250 minus IA is 2, RA is 0.5, so it is 249 volt, right? Now, when series resistance got introduced, it will be 2 into 3.5 plus 0.5, so it will be 4, so it will be 242. Now, can you guess what will happen after the insertion of resistance? Can't you guess even now? Now,
Yes, sir.
what will happen?
N2 will be smaller.
N2 will be smaller, exactly. So that's what will happen. So 249 into 1200. So N2 will be something around 1166.3. Okay. Okay. So this is what will happen. Any doubt in this?
No, sir.
Okay. Now what will happen to the load speed? This was the no load speed. What will happen on the load when you have provided 15 amps of armature current?
Sir, here armature current will remain constant 2 ampere.
Yeah, it is said that when the load is applied, the motor will take 15 ampere of armature current. So no load current was 2 ampere, but full load current is 15 ampere. So current has been changed, okay, but we still want the speed. Let me write it. The speed at full load. Can't you find EB3 again?
Sir, it
250
will reduce, sir.
minus. Yeah, it will reduce and it will reduce significantly. Minus 15 armature current into 3.5 plus 0.5, 4, right? So it will be 190 volt, isn't it?
Yes, sir.
Exactly. Now at this back
Yes.
EMF, what will be the speed? N3 by N2 is equal to EB3 by EB2. 190, 242, and 2 was 1166.3. So now just you have to calculate it and you will get around 915 point.
Yes, 915.69.
Yes, this will be your answer.
Sir, how did you calculate EB2? Just, sir, please explain me.
Yeah, EB2 we computed it with the same 2 ampere. The condition when series resistance got inserted in series with the armature resistance, at that instant 2 amps was flowing, but the resistance got increased from 0.5 to 3.5 plus 0.5, so 4, right? So 250 minus 8 is 242. Did you get this part?
No load model take.
It is very straightforward. See, the first condition when no series resistance was there. Okay, so 249 volt we got. 2 amps of no load current is flowing in the armature circuit.
Yes, sir.
Okay, now the next time when 3.5 ohm of resistance, let me write it at 0.5 plus 3.5. Now I hope it will be clear.
No, sir, I am not able to find the sentence that armature current is same both the cases.
See, we have to find the no load speed. At no load, armature current is given as 2 ampere, isn't it?
Yes, sir.
This 2 ampere is at no load, and at full load, 15 ampere. So these
Okay.
both conditions are for no load,
No load.
and this condition is for full load.
Okay, means at no load, whatever we will exert the resistance, armature have to
Yeah,
uh, take a 2 ampere current.
yes, 2 ampere current should be there.
Yes, sir.
Because there is no change in field or and the torque, load torque is also same.
Yeah, constant torque you can see here.
I think he missed that point here.
Okay, okay. Yeah, it happens sometimes.
Yes, sir.
So if you have any doubt, you can revisit it, right? That would be better. But I hope you must have got by now. Anyway, so this part you got, this third part, this portion at full load.
Yes, sir.
At yeah, at full load, 15 amps of armature current was there. Okay, and the resistance was 4 amp or 4 ohm, 3.5 plus 5, and we have two conditions, so we can find out the speed, right? So now the final question based on this part is what will be the speed regulation? What is the expression for this? No load minus full load by
No
full
load.
load.
Oh,
No
full.
load is it no load or full load? Actually, it is. It depends. It varies from book to book, but I consider it as a full load. So anyway,
Okay, sir. Let's go ahead with that.
yeah,
Sir, both
11.66.
case answer will come same.
No, no, no. In both cases, answer will not be same. But actually, this expression will help you in your competitive exam. Standard. I'm taking this expression as a gate exam as a standard because they whatever they will use, I think most of them will use. Or but even if you use both equations, both answers will be close, not exactly equal, but both will be close. But Actually, this is the standard what most of the people follow. That's why I'm following it. So
Yes, sir.
915.7 divided by 1166.26. So it will come out to be, 21.5%. So this is your speed regulation. Okay, any doubt in this part?
No, sir.
Okay, great. So now coming back to his question, what he posed in the starting. Okay. So let me just copy it.
Sir, I think now that is simple.
Okay. So that's why I told that we can deal it with in the end
But
of
sir,
the session.
once you can see,
Yeah, once we will discuss it. Yeah, definitely. I am bringing it on the screen. Okay, so this is what he had written. So 10 horsepower, 230 volt. Are you guys able to see this? Because I'm not able to zoom it. Let me see how to zoom it.
yes, sir, we are able to see.
Okay, just let me try it to increase the font. Okay. Now I hope it is pretty clear. So
Yes, sir.
what he wrote that 10 horsepower 230 volt DC shunt motor has an armature resistance of 0.2 ohm and field resistance of 180 ohm. Okay, fine. At no load and rated voltage, the speed is 1200 rpm and armature current is 5 amps. At full load and rated voltage, the line current is 60 amps and flux is reduced by 6% due to armature reaction effects from its value and no load. What is the full load speed? Okay. So we are talking about a speed here, right? So we should deal with in terms of back EMF. EV at full load will be, since it is a DC shunt motor, right? So 230 minus IARA. So line current is 60 amps. So what will be the field current? So let me armature current is field resistance is given 180 ohm. So what will be the field current? 230 volt by
1.27.
1.27. So this is your field current. And no load armature current is given 5 amps. So no load, okay, armature current is directly given. So we can directly take it, right? Armature current is 5 amps. 5 into RF, sorry, 5 into RA. RA is given 0.12. So it will be 230 minus 0.6. So 229.4 volt. Is it correct, right? At no load, right? At no. Now, at full load, okay, and rated voltage, line current is 60 amps and flux is reduced by 6%. So since flux is reduced by 6%, your field current should also be reduced by 6%. Okay. So initially field current was 127. Now IF2 we can write 0.94 into IF1. Does that make sense? It will be. Are you following, Deepak?
Yes, sir.
1.19
Sir, but
ohm. Yeah, go ahead.
sir, in question they are saying that we are applying rated voltage. So how
Yes,
can reduce the field current? Field current will be
by
fixed
varying the field resistance.
by varying the field resistance.
Yeah, that
Okay.
directly, see, they did not say how to reduce the flux, right? They said that they have reduced the flux.
Sir, armature reaction by.
by armature reaction, due to armature reaction effects from its value at no load. So armature reaction effects. Okay, so it means that some of the armature is, demagnetizing that field, right?
Yes, sir.
Okay, so let's say, but anyway, your field current will be 1.19 ampere.
Okay, sir, we cannot proceed with earlier was our flex was pi, and now our flex is 0.94 into pi.
Okay, so we cannot say that. Then what do you say?
Uh,
Flux is reduced
what,
by
sir?
6% means what?
Means our flex is 1.94 into earlier flex, whatever flex
0.94
was
into
earlier.
earlier flux. Yeah, yeah. But we cannot say field current. That's what you are saying?
Yes, sir.
Okay, okay, okay. Yeah. So actually, what I am saying that phi is equal to KIF. But
KI.
anyway, yeah. Oh, yeah, 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 exactly. So this what happens in series machine. IF2 is equal to. Okay, so if that is the case, then it is better to not include the current at all. Okay, so let us not include the current since we are directly given the flux. So phi 2 is given as 0.9451. Okay, and so now EB2 by EB1 is equal to phi 2 by phi 1 into N2 by N1. Okay, so it is nothing but 0.94 into N2 we don't know, N1 we know as 1200 RPM. Okay, EV2 we don't know. Okay, according to this condition, EV1 we know as 229.4. Okay, now sum of the armature current. So if field current is fixed, okay, if field current is fixed according to this statement, then EB2 will be equal to 230 minus 60 minus how much was the no load field current? Okay, no load field current was approximately 1 point something, right? How much was it, Deepak?
Yes, sir.
No load, no
Sir,
load field
1.27.
1.27.
1.27 amps. So 60 minus 1.27 into RA is 0.12. Okay, how much it will come out to be? 230 minus 60 minus 1.27 into 0.12. Is it 222.9?
Yes, sir.
Yeah. So this is your voltage at that instant. So assume, so see, according to this logic, what question have provided, at this current, 60 minus 1.27 amps of current, okay, there is some demagnetizing effect is happening. What does the question mean by demagnetizing? That I field is constant at 1.27 amps, right? But flux is getting reduced. So it is getting reduced by means of
Demand.
armature current. So there will be some NIA which will oppose the flux, right? So let me take this is the IF, okay, and this is your quadrature axis. This is your GNA, right? And this is your magnetically neutral axis. Okay, so this is the axis of your armature current. Okay, now this armature current will have some component along the GNA, IA, Q, or let's suppose IA torque producing or cross magnetizing. It's a perfect term is cross magnetizing, which textbook also use.
Cross magnetizing.
And this component will be demagnetizing.
Demagnetizing.
So according to the question, this is what happening. This demagnetizing component, though it will be very small, but it is demagnetizing it by that much 6% of the rated flux so that it can operate at that particular speed or because of brush shift. You got the point of this demagnetization?
Yes, sir. And sir, our GNA will never shift anywhere.
GNA is fixed. It is fixed at the cross magnetizing point, right? This is the point which is fixed. What the shift is your magnetically neutral axis.
Okay.
Okay, so this is
Okay, sir.
what will happen, and because of this, shift, if you read the theory, why does it happen? To avoid the sparking, right? Avoid the sparking in the brushes. We have to
Yes, sir.
shift multiple times this MMA. And because of this, that rated flux will be reduced by the demagnetizing. What happens in AC machines? In AC machines, in permanent magnet machines, in synchronous machines, we we control in permanent magnets. We cannot control the flux that is originated from the permanent magnet. So to demagnetize it, we provide some armature current in that opposite direction, in this direction. So this is what
Yes, sir.
essentially happening here as well. So now we have ended up with the back EMF of 222.95. So let's see what will be the speed. So from this equation, okay, N2 is equal to EB2 is 222.95 divided by EB1 is 229.4 into 1200 divided by 0.94. How much it will come? 2.95 divided by 229.4 into 2.94 into 12. So see, it has gone in the field weakening zone. This value is coming out to be 1240.7 RPM. Okay, so at this speed with this phenomena, it will run. Any doubt in this particular problem?
Sir, here we cannot go with the current. Sir, I did with this IF reducing. So my answer was coming around 3000 RPM.
1300
That
RPM.
was
Okay.
wrong. That was
Yeah,
wrong,
yeah,
I
yeah.
think.
Yeah, because if you reduce the field current, since you pointed out initially very perfect point that it is getting reduced by armature reaction effect, not by field current reduction. So that is our general tendency to just go ahead with, as we are changing, we conveniently reduce the field current. But yeah, you should consider this particular statement was very, very dominant. If you overlook this, then we are gone. That's what I did initially, right? and that's
Yes,
our
sir.
general tendency to go ahead with.
Tendency.
Yes.
Okay, sir. Thank you, sir.
Yeah, thank you very much. So I guess that's all for today. I do not have any more questions. So I guess it will be sufficient to solve the problems based on it. And you got enough information about it. And you just keep practicing. Okay. That's the way to regain the concept in your memory. So thank you very much for joining. If you have any final question, you can ask or we can leave it. So,
Sir, in practically when we applied the load, electrical power, there will be always constant or it will increase.
electrical power will be always constant or increase. What are the conditions you are providing? It depends on that. Okay. So first thing is that uh, you cannot deliver constant power at all the speeds after base speed. Okay. And below base speed, of course, your power is increasing. So at base speed, what is your rated power that you have to maintain it after base speed. So after base speed, maintaining power is a bit tricky, okay? But you can maintain it up to certain speed. That is why it is known as, constant power speed region. So this factor, constant power speed region, is very important factor when you design some machine for any particular EV applications, right? But yeah, it has some limitations. As you increase the speed, your frequency dependent losses will increase. So I hope you understand by frequency dependent losses, like iron losses. Okay. Some other
Eddy
losses are
current.
also, and you increase the speed, you are increasing the mechanical losses as well. Like aerodynamic, drag, and all will come into picture.
And sir, in this question, 10 HP is a output shaft power. They always give output shaft power, not input.
Yeah, every time in question it will be provided by output power. These ratings are based on output power, not based on input powers.
Okay, sir, it will take that much amount of power.
No, it will produce that much amount of power. It is a motor, right? Even generator
Yes, sir.
also, it will produce output power of 10 HP. So
Yes.
its input will be some losses plus this output power.
Okay. Input power is not fixed. It will variable.
Yeah, it can vary. It can vary because if you are supplying by a battery or DC link capacitor, so it will vary.
Okay. Yes, sir. Thank you, sir.
Okay, you are welcome.
No,
So
sir.
shall we wind up?
Okay, sir.
Yes,
Okay, great.
yes, sir.
Thanks for joining. See you on the next Sunday. Bye. Good night.
Good night, sir.
Bye, sir.
Bye.